Hi, welcome to me313 Mechanical Engineering Thermodynamics. The topic of this video is the ideal Brayton cycle. The section in Sengel and Bowles is section 9.8. So here are the learning outcomes. At the end of this video, you'll understand the major steps that make up the Brayton cycle. You'll be able to draw the Brayton cycle on a PV and a TS diagram. You'll know the assumptions that go into the ideal cycle, and you'll be able to solve for the states and the thermal efficiency of the Brayton cycle. So here I want to go ahead and discuss what are the basic components of the Brayton cycle. The Brayton cycle uses gas. This is a continuous cycle. It has a compressor and a turbine, and then we have a heat exchanger. So the air comes in at some low pressure and temperature. Usually this is like atmospheric air. Goes into the compressor up to a high pressure. There's a slight increase in the temperature during this compression. And then we go into a heat exchanger. This is essentially just a large burner that goes ahead, and often they're gas-fired burners or oil-fired burners, depending on what the cheapest fuel is at the time, heats the fuel up, and usually this occurs at more or less constant pressure, and the ideal Brayton cycle will assume there's no pressure drop. And then we'll take this hot gas that is pressurized, run it through a turbine to go ahead and generate some work, and then it will go ahead and exhaust. Now, if this is just an air mixture, often this is just exhausted into the atmosphere, and then we bring in new atmospheric air. We can kind of simulate that as a heat exchanger. Nuclear power plants tend to use gases other than air. They might use helium, for example, or argon, in which case there will be a heat exchanger here because we want to conserve that working fluid. So let's go ahead and draw this cycle on a PV diagram. And so we'll just start off with state 1 over here, which is at a relatively low pressure, and that'll be 0.1. And then we run in through a compressor. And so the compressor is going to go ahead and increase the pressure and decrease the volume. So it'll go up and to the left. And then we're going to go ahead and run through the heat exchanger where it heats up the gas. And the ideal cycle, this is not really any significant pressure drop through there. So this is straight across to 0.3. And then we run through the turbine where we're going to again drop down to the lower pressure, which would be 0.4. And then, as I said, we may go ahead and run through a heat exchanger or just go ahead and exhaust that gas out and bring in new air right over at this point right here. So the QN state is right there, where we're heating the gas from 2 to 3. We've got work going out at this point, but we've also got work going in here, and so the net work is going to be the difference between those. And we also have seen before that the net work is the area underneath this PV diagram. This step right over here would be simulated as Q out, again depending on whether it's exhausted or just runs through a heat exchanger. Now let's draw the same thing, cycle on a TS diagram. And so now on a TS diagram, again, we're going to start off at a low temperature. This will be 0.1. And we're going to go ahead and run through a compressor. The ideal cycle is an isentropic compressor. So this is going to be vertical. And compression results in some increase in temperature. So there would be 0.2. Then we run through a heat exchanger at constant pressure. It's going to go ahead and increase the temperature and at the same time increase the entropy. And so it'll go up to some point up there, which would be 0.3. Running through a turbine, if this is an isentropic turbine, it's going to go straight down to 0.4, and then we can go ahead and connect 4 to 1 again. Either maybe it goes through an exhaust or it runs through a heat exchanger. Remember again, the area underneath the TS diagram also represents the net work. Step 2 to 3, that's where heat is added, and 4 to 1 is where heat is leaves the system. All right, so there's the ideal cycle. The ideal cycle, we're assuming we've got isentropic turbines and compressors, so those right there are going to be vertical. We can derive an equation for the thermal efficiency, similar to like we did for the Otto cycle and for the diesel cycle. We'll find out it's actually a somewhat simple equation if we make some assumptions, such as a constant heat capacity. And so let's just go ahead and remember that the thermal efficiency of all cycles is going to be the net work normalized by the amount of heat that we put in, and we can go ahead and rearrange that to 1 minus Q out over Q in by applying an energy balance over the entire cycle. Now, if we go back and look at the Q out and Q in steps, right over here, right, Q out is going to be 4 to 1, Q in is going to be 2 to 3, and so we can go ahead and look at what that is. And we can write that in terms of CP, those are constant pressure, this is an open system, and Q out is going to be T4 minus T1. And then the heat in step, Cp, this was equal to T3 minus T2. So we have a somewhat simple equation. It's actually going to look a lot like we had for Otto cycle. So I wrote my little 1 minus there, 1 minus those terms, and the Cp's are going to go ahead and cancel out. So now I've got 1 minus T4 minus T1 over T3 minus T2. We'll do a little bit of rearrangement like we did before with the Otto cycle. I'm going to go ahead and factor out my T1 on the top and my T2 on the bottom. So I have 1 minus T1, T4 over T1 minus 1. Just factoring that out, and I'm doing the same thing on the bottom here with T2. So I have T3 over T2 minus 1. And the reason I did that is because I'm going to go ahead and do some more rearrangement with these ratios, like the T1 over T2. So again, let's look at T1 to T2. That's running through, through the compressor from a low to a high pressure. And so if that was isentropic, and we assume a constant heat capacity, T1 over T2 for isentropic compression is going to be P1 over P2 to the K minus 1 over K. And same thing for the turbine, 3 to 4. And so I can go ahead and write T4 over T3 is equal to P4 over P3 to the K minus 1 over K. And that's kind of nice because, see, here's this ratio of T1 over 2. There's a T1 over T2 ratio. I have a 4 over 3 ratio. Right there's a 4 over 3 ratio. And again, a 1 over 2. So there's some simplification that ends up happening. And so we find out that the thermal efficiency of this cycle is 1 minus 1 over, and it's called the pressure ratio, R sub P, to the K minus 1 over K. And so the pressure ratio is defined as the high pressure over the low pressure. So in this case, this would be the same as, for example, P2 over P1, which would be the same as P3 over P4, so the high pressure. So in the Otto cycle and diesel cycle, we had a compression ratio, which is just R. Here we have a pressure ratio, which is symbolized as R sub P. And again, it's the ratio of the pressures. A couple things in terms of ways to increase the efficiencies of the cycle. So first on the left, I have a plot of the efficiency of the Brayton cycle as a function of the pressure ratio. This is just a plot of this equation right here. And what you realize is that as I increase the pressure ratio, I'm going to go ahead and increase the efficiency. There's some sort of decrease in or law of diminishing returns in here, but my pressure ratio can be anywhere from 5 to 20 would be typical for most power generation cycles. It seems like you might want to just go ahead and keep increasing the pressure ratio, but it turns out there's some other limits that happen with these gas cycles, and so it kind of helps to, let's start off, and I'm going to draw this cycle on a TS diagram we had before. Right, so right there might be my cycle, and this is my pressurization 1 to 2. And so if I increase the pressure ratio, maybe I would end up going to, say, that point right there. And if I keep everything else the same, I'd be adding the same amount of heat. So I would end up at that point right there and dropping back down. And clearly I'd be generating some more work because the area would be larger. But notice what happens every time I increase the pressure ratio and keep everything else the same, this temperature keeps getting hotter and hotter and hotter. And there's actually going to be a material limit of what my system can handle. If I get too hot, I'll actually melt my turbine blade. So normally there is a Tmax, which is a material limit of how hot I can be. And I'm actually going to be limited to that point. So I can adjust my pressure ratio, but my final temperature can never get any hotter than that. So now if I look at a couple extremes, and I'm going to use that same diagram, but I'll change my pen color. So for example, now if I did a high pressure ratio but was limited by Tmax, my plot would look like that. And if I went with a really low pressure ratio, let's do that one in maybe purple. This would be a very low pressure ratio, and again working with Tmax. I would have an area that looks like that. Now notice this area, this purple area, is pretty small relative to the red one, and the green one is actually a little smaller than the red one. There's actually an optimum temperature or pressure ratio in there given a given Tmax, and actually it's a function of Tmax over T1. And so there's an equation for that, and actually what it is right here. So the maximum, or the optimum, I should say, optimum pressure ratio is T high over T low. So it's this T max. I call it T max. You could also call it T high. T max over T low, that would right over here. This would be T low, function of that, and then the ratio of K over 2K minus 2. So that's going to go ahead and give you the optimum value. And this is often maybe like 12 or 14. It's somewhere in the middle. But here's a way you can go ahead and find out what the optimum pressure ratio is given a given inlet and outlet temperature. All right, so let's go ahead and do an example here. We'll just do a straightforward example. We have an ideal Brayton cycle. We're going to be using air, so we're going to have a value of K, which will be 1.4, and the value of CP, that is about 1.005. And we got our low pressure is 100, our high pressure is 2 megapascals, so that tells us that our pressure ratio is equal to 20. And we've got an inlet temperature of 27, an outlet of 727, and those come up to some nice round numbers of 300 Kelvin, and this will be 273. That's going to give me 1,000 Kelvin right over there for T high. So let's go ahead and calculate what our thermal efficiency is. And so I always think it helps to kind of just sketch up my PV and TS diagrams to remind myself what these cycles look like. 1, 2, 3, 4. Let's do a TS diagram as well. 1 to 2 to 3 to 4. And so point 1, we're given point 1, that's our low pressure and our low temperature. So that's going to be 100 kPa and 300 Kelvin. And so we can just go ahead and go up to point 2, and we can find out point 2. This is through the isentropic compressor. So T2 is going to equal to T1, P2 over P1, and this is K minus 1 over K. My K is 1.4. I've got my inlet temperature. Make sure you put Kelvin in there, and that number right there is going to be 706 Rankine. And we can do the same thing going from 3 to 4 because we're given the high temperature is, it's 727, and we're told what the high pressure is as well. So I can go ahead and find out what T4 is. T4 is P3, and that's going to end up being equal to, this is P4 over P3, the K minus 1 over K, and to give myself T4, and that right there is 425. I'm sorry, that's, I said Rankine after this is Kelvin. That's in Kelvin as well. All right, so now I have all of my temperatures, so I can go ahead and find out what my thermal efficiency is, because eta is going to be 1 minus Q out over Q in. So let's find out what Q out is. And Q out, that occurs at that step there. So that's going to be CP T4 minus T1. And if I plug in those numbers there using my value of CP of 1.005, this is 295.5. My units are going to be kilojoules per kilogram, going from mass here. And then Q in, CP, Q in step is 3 to 4, so T3 minus T2. And I plug in those numbers, that's 125.6 kilojoules per kilogram. So let's go ahead and calculate our thermal efficiency. Q1 minus Q out, which is, sorry, did I mess up those? This is, oh, I'm sorry, this is Q in, and this right over here is Q out. I got those numbers backwards right over there. So these, actually, these two numbers right here should be swapped. This right over here is Q out, and this one right over here is Q in. So again, Q in is going to be 3 to 4, but sorry about that. Let's swap those. But if I do 125.5 and then normalize that by 295.5, I get an efficiency of this one right over here of 0.57. So it's 57% efficient. So that's the efficiency of this ideal Brayton cycle. Now remember, the ideal Brayton cycle, we had vertical from 1 to 2 and 3 to 4. And so what happens if we had something that's sort of inefficient? So if you remember the isentropic efficiency that we discussed in chapter 7, so for example, let's look at a compression going from some point 1 to point 2, that would be isentropic, and it's going between some pressure limits of P low and P high. So there's P low and there is P high. And if I had an inefficient compressor, it would actually go up to this point right here. So this would be 2 actual, sorry, 2s, and this right over here would be 2 actual, right? And so if everything else was the same, we'd go ahead and go up to a point there. Maybe we had an isentropic turbine going down there. And what you realize is you clearly went ahead and reduced your network area, right? You lost this right over here. So you have a loss of efficiency. So we can go ahead and calculate what our change in efficiency is if, for example, we had some inefficient compressor or turbine. So let's return to the problem that we had, but now we're going to say that the compressor is 90% efficient. So the efficiency of the compressor is 0.9. And so that, remember, if we come back here and look, what we're looking at is this distance and this distance, and we want the efficiency is going to be that distance over that one right there. So this is going to be 2s and 2 actual. So this right over here is now going to be h2s minus h1 over h2 actual minus h1. And if we have a constant heat capacity, that's going to end up being Cp, and this will be T2s minus T1, Cp T2 actual minus T1. And so we're going to need to determine what is T2 actual. And so T2s, well, we got that from our previous problem. That's 706 because that was the isentropic one. So this is going to end up being 706, and T1 is 300. T2 actual that we want to find minus 300. So let's go ahead and solve that, because that again is all equal to 0.9. To give myself a T2 actual, and that right there is going to end up being 751 Kelvin. So now if I look, this is going to be changing my Tn. So here's my Qin step right there. It's changing Qin because I'm actually going to be adding a little bit less heat in that step right there. So Qin is going to end up being equal to Cp T3 minus T2 actual, and that comes out to about 250 kilojoules per kilogram. And so now let's go ahead and get our new thermal efficiency, 1 minus Q out, and the Q out step didn't change. We went ahead and, if we look at this, we were just doing the compressor, so the Q out state right there didn't change. So that's 4 to 1. So that number is not going to change, and so that's still going to end up being equal to 125.5. But now Qin is equal to 250, that number right there, and that efficiency is 0.5, so 50%. So what we realize is going from 100% isentropic efficient compressor to 90%, we dropped our efficiency from about 56% of the thermal cycle down to 50%.